All right, good morning again. We'll go ahead and get started with exam review. So this exam coming up this week, it's going to be available tomorrow. We'll cover chapters 7 and 8. So I'm focusing more of our exam review on chapter 7 because we'll be reviewing chapter 8 concepts throughout the lecture for chapter 9. So it's a little bit chapter 7 heavy. We're starting out with predicting whether a precipitate will form as a result of a reaction. So these reactions are potentially double replacement reactions. We're taking two solutions, mixing them together, and seeing if we form something that is insoluble. So for the first one, since we have our two solutions and we know it's kind of like, okay, you mix them together and see what happens, we've got to switch the positive ions. So the magnesium, instead of being partnered with the sulfate, is going to be partnered with the chloride. And notice that I'm not writing anything in yet for the state of matter because I need to figure that out using my solubility rules. So I switched the partners for the magnesium, and now I've got to do the same thing for the sodium. Then I look at my solubility rules. So I've got magnesium chloride and I've got sodium sulfate. So I find on the chart where I see something about these ions. So Cl, that's a halide, and they are generally soluble. But let me make sure that I don't have an exception. So the exceptions are silver, mercury 1, and lead 2. Those are insoluble. Well, I've got magnesium chloride, so that should be aqueous. That's soluble. For sulfates, they're also generally soluble. And I've also got the sodium ion, which is also generally soluble in water. Since what I would form is two soluble compounds, what this really means is that there's no reaction because both of these compounds are soluble. So no precipitate here. Any questions on that one? Then we'll go ahead and go over the next one. We have to do the same trick where we swap the positive ions and see if we form something that is insoluble. So we've got silver acetate and strontium iodide. We're going to switch partners. The silver will now be with the iodide. And then the strontium will be with the acetate. Now we need to use the solubility rules to see where we are. So again, iodide, that's a halide. They're generally soluble. But there are exceptions, and silver is an exception. So this compound will form a solid. Let's check the other compound just to be sure. We've got strontium acetate. Acetates are soluble, and there's no exceptions here. So we do form precipitate. It is the silver iodide that forms a solid. And that's it for these. Questions about using solubility rules or predicting the products? I'm going to guess it's a no. Good morning, y'all. I know it's early. So now we've got an activity series question. You have to predict whether each of the following metals will react with sulfuric acid. I will give you about a minute to do this one, and then we'll go over it. With this question, you have to remember how to use the activity series, which I've put on the slide just in case you didn't have it in your notes or you didn't feel like rifling through your notes. You'll be provided with the activity series, so you don't need to memorize it. You need to figure out where each of these metals are in relation to where hydrogen is. Here's hydrogen. I'm going to mark all of these. So hydrogen is here. Everything that comes before hydrogen in the activity series will react with sulfuric acid. Everything that comes after will not. The silver comes after. So there's no reaction here. But tin, cobalt, and manganese are all before hydrogen in the activity series. So that means that all of these metals will react. How do we do on that one? Good. This is a gas density question. Since this isn't specifically in Chapter 9, I figured I'd include a question like this for us to go over together. So I will give you 2 minutes to start it, and if you don't finish it, that's okay. I'll go over it and make sure that we all get it, and then we'll move on. Hopefully you've had time to set up the problem at the very least and figure out if you're going to get stuck. That's kind of the goal here, to see what you remember, what you don't, and then we kind of get you back on the right track. We've got an unknown gas, mass of 25.4 grams, volume of 15.9 liters, and it's at STP. We need to figure out the molar mass. This is a gas density question. Now, I know we're not being asked to figure out the density, but we need to use our definitions of density for gases to figure out the molar mass of this gas. In Chapter 2, we talked about how mass is defined as, or density is defined as a mass divided by volume. And in Chapter 8, we also said that for a gas at STP, the molar mass of that gas divided by the molar volume will also get us to the density. So the first step is to solve for the density of the gas using the mass divided by volume. We're given the mass, 25.4 grams, and a volume of 15.9 liters. Make sure that when you do this calculation that you have grams over liters, because that's what the units are for density of a gas. Now I'm carrying a lot of digits here because we're not concerned with sig figs yet. I carry a lot of digits just to make sure that I don't have any kind of rounding error when I move on and do my next calculation. Now we can solve for the molar mass using our special density equation. And remember that molar volume is 22.4 liters. That's a definition that we talked about in Chapter 8. And when you solve, you multiply both sides by 22.4. And that is your molar mass. How did we do on this one? Are there questions? Did you get it? Were you close? Talk to me about how it went. Okay, we got a couple folks who got it. Good. If you're just kind of sitting back, taking it all in, that's cool. But at some point, I want to hear from you because I like to check in and see how we're doing. So now we've got one of these molecular formula percent composition type questions. I'll give you another 2 minutes or so just to get started. This one is from the exam review. So if you've already done the exam review, you've already done this problem. But we can go over it as a class. So I'll give folks a couple minutes who may not have done the exam review, and then I'll start going over it. If you're still working on the problem, that's cool. I'm going to start setting up here. We've got mercurous chloride. We know the molar mass and the percent composition. We've got to figure out the molecular formula. When we're given the percent composition, we have to assume that we have 100 grams of the substance. That way those percentages become more useful and we can say grams. The first step is to take the grams and convert to number of moles for each element. That's it for mercury. Then we take the 15 grams of chlorine and do the same thing. So that's the number of moles of each element in this compound. We're now going to figure out the mole ratio so we can figure out the empirical formula of the compound. Both of these are about the same, 0.424, 0.423. We know that the ratio is going to be 1:1. But I want to write it out just for completion's sake. So you put the smallest number of moles on the bottom, and then you put everything else on top. That's going to be about 1, right? And what that means is you have 1 mole of mercury for every 1 mole of chlorine. The empirical formula is HgCl. Not done yet. We now need to figure out the molar mass of our empirical formula. You add together the 200 some odd grams plus the 35 some odd grams to get about 236 grams per mole. Then we figure out how many times we need to multiply our empirical formula by to get the actual molecular formula. So we take the molar mass of the molecular formula and divide by what we just calculated for our empirical formula. And that's about 2. So that means we need to take our empirical formula and multiply it by 2. That's our molecular formula. Questions here? So you may not get one that's this simple, where it's just 1-to-1. So make sure you understand how to do the empirical formula when you have more than just 2 elements, when you've got, different numbers of moles, all that good stuff. Here's the final question. I'll give you a couple of minutes, and then I'll check back in. All right, hopefully you had a chance to at least get set up and figure it out a little bit. Now it's my turn to help you out. So this is one of those mass to volume questions. We're given the mass of a gas, and we have to figure out the volume at STP. We made a little bit of a cheat sheet where we could figure out how to get from one unit to another. And we can't go directly from mass to volume. So we have to do 2 small problems. The first one is where we go from mass to moles. The second one, we go from moles to volume. To go from mass to moles, you've got to use molar mass. I'm not going to show you how to calculate the molar mass, but hopefully you remember, because that's chapter 8. But you sum up the masses of all the elements in the compound, C2H6, and you should get somewhere in the ballpark of 30. When we write out our unit factors, this is what they look like. Now to get from moles to volume, we have to use molar volume. That only works at STP, where 1 mole of gas has the volume of 22.4 liters. Now that we have all of our unit factors worked out, we can put the whole equation together. We're trying to go from grams to moles and from moles to liters. Those are the units that we need to carry through to get to the promised land. We're starting with grams in the numerator. To get rid of that and end up with moles, we've got to put grams in the denominator. Then we have to get rid of moles and be left with liters. So the moles have to go in the denominator for the second unit factor. Always do the unit analysis to make sure that you end up with the right unit. So we got to moles, and then we got to liters. Then you do the calculation. 7.5 divided by that molar mass multiplied by molar volume. You should get 5.59 liters as your final answer. You'll definitely have to do some of these on the exam. And because the exam is online, it may be a little bit tricky to show your work. But here's what I want to talk about. This kind of leads us into talking about the exam. So for these types of problems, to show your work, what you can do is type out this part so that I can see what your final equation was. If you feel like you can't get here, but you know that you can write out unit factors, then do that. And you'll at least get some partial credit if they're the right unit factors. Okay. So let's say that this problem was worth 10 points. If you're just like, look, I know it, I got it, I'm going to put the answer, fine. If it's right, you're good. If it's not, you don't get any credit. Let's say that you showed me this equation and you got all of the equation right, but maybe you wrote, you typed something in your calculator wrong and you got the wrong numerical answer. If it was 10 points, if you gave me just this piece, then that translates to about 7 points. This is the majority of the work right here. So it's really important for you to show your work if you want to get partial credit, because sometimes it is just a matter of, oh, I typed it in the calculator wrong. Now let's say that you couldn't put this equation together, but you got the unit factors. You got to show me both unit factors for both of the parts of the equation. For both unit factors, both sets, you would get about 5 points. About half credit. You knew how to get there, sorta, kinda. You did some of the work, but you didn't get over the hump to put an equation together. So this can be the difference between passing and failing an exam. Are there any questions here? Okay. Then what we're going to do is we're going to take a short break, and then we'll move into Chapter 9. So we'll take about a 10-minute break. We'll say 8:55. Shake your brain out a little bit. Make sure you don't have any questions about the upcoming exam. And then we'll get started with Chapter 9. All right, everybody. It is 8:55. So it's time to get back to it. Unless there are any pressing questions about the upcoming exam, I think we should just dive right into Chapter 9. So let me know. Questions? Or can we move forward to Chapter 9? Okay, go for it. So the exam will be available tomorrow by 9 a.m. Okay. So, and then there's a question on the exam review. So, how is that one a solid? I'm just going to go back to that slide. Okay. So, up here we have the things that are generally soluble, right? So, one of the things that falls under that umbrella is the halides. Generally, they're soluble. But there are some exceptions. If you have silver, mercury 1, or lead 2, those things are insoluble. And what we had was silver with iodide. So if that X is equal to any of the halides, Cl, Br, or I, then you're going to have something that is insoluble. Does that help answer your question? Okay, great. Yes, there will be a calculator on the exam. I enable the scientific calculator. So if you don't have one, you can use the one through Respondus. So exam 4, it'll be available for you by 9 a.m. tomorrow morning, and it'll be available until 11:59 p.m. on Friday. So you have to at least start it by then. The equation sheet for exam 4 is already posted. If it's not, I'll get it posted today. I remember thinking about it, but I'm like, did I post it? Now I don't remember. But it'll be posted today, along with a select answer key for the Chapter 7 problem set, the practice problems. All of those things should help you prepare for the exam. I also have office hours today from 11:30 to 1. So if you have other questions that you realize, after class or something like that, you can come on by, ask your questions. All right. So with that, we are in Chapter 9. Chapter 9 builds on Chapters 7 and 8. So we're just going to do a quick recall on interpreting a chemical equation and build from there. We've got two gases here, nitrogen gas and oxygen gas. You combine them, you heat them, and you make nitrogen monoxide. The numbers in front of each of these compounds tells you the ratio. When you don't see a number, you just say that it's 1. So I could interpret this equation as 1 molecule of nitrogen gas plus 1 molecule of oxygen gas combine, and they're heated, to make 2 molecules of nitrogen monoxide. The other interpretation that we can use, which we're going to use for this chapter, is instead of saying molecules, we can say moles. If I have 1 mole of nitrogen gas and 1 mole of oxygen gas, I form 2 moles of product. So these ratios, the numbers in front of the compound, can be used to determine amounts. This is the interpretation that we're going to use. And that's what this slide says. We can use a balanced chemical equation to write mole ratios. And we can use those as unit factors. So using the same exact equation, we're going to learn how to write mole ratios. They're also called mole-mole factors, mole-to-mole ratios, a whole bunch of different names for the same thing. All we're doing is using the balanced chemical equation to write a relationship between 2 compounds within the equation. So what does that mean? Let's say I want to write a mole ratio that talks about how much nitrogen I need to make the nitrogen monoxide. What I would do is look at the chemical equation for the coefficients in front of each of these compounds. For the nitrogen gas, there's no coefficient, so we say it's 1. I write 1 mole of nitrogen gas. It's a unit factor, and remember those look like fractions. So I can put that in the numerator. Then I look at the equation for the coefficient in front of the nitrogen monoxide, and it's a 2. So I write 2 moles of nitrogen monoxide. And that is a mole ratio. For every 1 mole of nitrogen, I make 2 moles of nitrogen monoxide. I can also write the reciprocal. And those would be my mole ratios. Now let's do that between the oxygen gas and the nitrogen monoxide. There's a 1 here in front of the oxygen that's implied. So we write 1 mole of oxygen gas. And on the bottom, still the same 2 moles. We're just writing the coefficients from the problem, or from the equation, in the unit factor. And then you write the reciprocal. What I would like for you to try is to write a mole ratio, or the pair of mole ratios, between nitrogen gas and oxygen gas. If you are feeling like a challenge, you can type it in the chat if you'd like. Or you could even just put the numbers, as a fraction. But I'll give you maybe about 30 seconds to kind of think about it and put it into the chat. Or not. You can at least maybe think about it or put it in your notebook. Yeah, it would be 1 to 1. Now it's really important to keep the unit straight here and write moles of whichever compound, because we're eventually going to be using these to do calculations. So let's do a bit more practice with writing mole ratios. I want you to write the 2 mole ratios for mercury 2 oxide and mercury. So that's this and this. I'll give you a minute and I'll check back in. Okay, that was a little bit more than a minute. We've got to write 2 mole ratios for mercury 2 oxide and mercury. You look at the chemical equation, make sure that it's balanced, and then all you do is write what you see. So how are we feeling about mole ratios? Writing them. Do we need more practice? Or do we want to try using them? Yeah, it's a pretty simple thing. But don't worry, we'll build on it. So I have another example that I'll just walk through real quick, just in case, for the people in the back. 2 mole ratios between mercury 2 oxide and oxygen. 2 moles because we see the 2 for the mercury 2 oxide, 1 mole for oxygen gas because there is no coefficient in front of it, so we just say it's a 1. Once you have one of those mole ratios, all you got to do is flip it. Now we're going to do mole to mole calculations. And what that really means is if I know how many moles of, say a reactant that I'm starting with, I can figure out how many moles of product I should make. So in this example, how many moles of oxygen gas are produced when 3.5 moles of mercury 2 oxide are decomposed? So let's put this in perspective. What we have is 3.50 moles of mercury 2 oxide. And we have to figure out how many moles of oxygen gas. To rewrite the question, for these kinds of calculations, we use those mole ratios that I was just showing you how to write. We know how many moles of mercury 2 oxide we have, and we need to figure out how many moles of oxygen gas will be produced. We need to write a mole ratio that relates mercury 2 oxide and oxygen gas. And we just did that. That was by design. Those are the 2 mole ratios that we can write between these 2 compounds. Just like in Chapter 8, you have to write out your units. So just writing 3.50 moles isn't enough. Moles of what? Mercury 2 oxide. Now we need to put in one of our mole ratios. We're trying to figure out how many moles of oxygen gas we'll make. Which one of these unit factors, if we multiply through, would give us the units that we actually need, which is moles of oxygen gas? A or B? Just like in Chapter 2, once you have the unit factors, you choose which one you need to get from where you are to where you want to be. When we do the math, you take 3.5 and you divide it by 2. Questions here? So I want you to try it on your own. How many moles of mercury 2 oxide decomposed to produce 5 moles of mercury? So I'll kind of get you started here. We're looking at these two. And our question is, we've got 5 moles of mercury. How much mercury 2 oxide did we start with? I'll give you 2 minutes, and then I'll check back in. All right. So we have our question set up. We have to write the mole ratios. We're looking at the relationship between mercury 2 oxide and mercury. You simply write what you see. So which one do we need to use, A or B, if we need to go from moles of mercury to moles of mercury 2 oxide? So in this problem, yeah, 2 over 2, that's 1. I get it. Not really a huge deal about units. But when we make these problems more complicated and we add on to them, it will absolutely matter. So just get in the habit of writing out your unit factors, your mole ratios, and writing out the units in the equation that you set up to solve your problem. It will save you a lot of points and a lot of headache. It's a lot easier for a tutor to help you or for me to help you when you write out your work, because then I can tell you where you went wrong. Let's do one more. So you'll notice that all of these are gases, and that's okay. We're still dealing with moles. Doesn't matter if it's solid, gas, whatever. How many moles of hydrogen chloride gas are produced from 0.75 moles of chlorine gas? So I'll give you a minute or so to try to set this one up, and then I'll jump back in. First step with these mole to mole calculations is always writing out the mole ratio. Once you've set up your problem, restated your question, you write those mole ratios. There's no coefficient in front of the chlorine gas, so you write 1. There's a 2 in front of the HCl. You write that as 2 moles. Then you write the reciprocal. Starting with our number of moles of chlorine gas, we've got to figure out which one of these we need to use. We need chlorine gas in the bottom. It's going to be B. To do the math in your calculator, if you need to, it's 0.75 times 2. And there we go. So this seems like a simple concept, and it is. This is the center for all of the stoichiometry problems that we're going to be doing for the rest of Chapter 9. If you understand this part, then the rest of the chapter is pretty much adding on concepts from Chapter 8 to these mole-to-mole calculations. There's 3 types of stoichiometry problems. We're going to try to get through 2 of them today. We're going to start with mass-to-mass stoichiometry problems. And I'm telling you kind of the names of them because the biggest problem that I see that students have is identifying the type of problem so you know how to solve it. So that's always my goal. I want to help you problem solve. That helps you develop your critical thinking, and you can apply it to other things. I'll give you an example of a mass-to-mass problem. So I'm using the example from the video, and then we'll do some more problems together. And this is a mass-to-mass problem. What is the mass of mercury produced from the decomposition of 1.25 grams of orange mercury 2 oxide? So this is the same equation that we've been working with, and I kind of did that by design. So we already have an idea of how to write the mole ratios for these. We're familiar with them. Now we can add on to it. What is the mass? That tells you that we're looking for a mass of something, right? We're looking for the mass of mercury. And we're told what we're starting with. 1.25 grams of mercury 2 oxide. And that's what we're given. What we need to figure out is the number of grams of mercury. When you have a mass and the question is asking for the mass of another component of the reaction, it's a mass-to-mass problem. You're converting the mass of one thing to the mass of an unknown thing. The generic equation that we use for this is as follows. We've been given the number of grams of A. we need to turn that into moles. We need the molar mass of A. We need to convert the moles of A to moles of B. This is where the mole ratio comes in. And it's always going to be in the form of B over A. And that will make more sense once I assign A and B to our problem. Since we have to figure out the mass, that means we have to get to grams of B. And that's going to be with the molar mass of B. In our problem, the given information is your A. So that means everywhere that you see A, we're calling that mercury 2 oxide. Everywhere that you see B, that's our mercury. So to rewrite our plan, we're going from grams of mercury 2 oxide to moles. And we need the molar mass of mercury 2 oxide to do that. We go from there to moles of mercury. Our mole ratio is going to be the number of moles of B over the number of moles of A. So that means when we're writing our mole ratio, it needs to be the mercury over the mercury 2 oxide. And finally, we need to convert the moles to grams. You need the molar mass of mercury to do that. Let me know if you're still with me so far. All we did was write out a generic plan, and then we added in what we're actually doing. So I would recommend, if you don't already, get this into your notebook. For every mass-to-mass problem, you can use this generic method. Assign your A, assign your B, and then you can write your plan and solve the problem. Now we need to set up the equation. That's what we're starting with. We need to convert to moles. Now in this problem, we were given the molar mass, which is very nice. Don't count on that happening all the time. Oftentimes you will have to calculate the molar mass for the compounds that you're dealing with. Next is the mole ratio. And we said for this, it's going to be B over A, what we need over what we're given. Our B is mercury. So you look at the chemical equation, and you see 2 moles of mercury. That goes in the top. Go back to the equation for the mercury 2 oxide. That's our mole ratio. We have to convert the moles to grams. So you write the number of grams of mercury in 1 mole in the top this time. And that's just straight up from the periodic table. Always go through and check your units. You can check them against your plan because your plan has all the units that you're trying to jump to. We started with grams of mercury 2 oxide. And we got to moles of mercury 2 oxide. Then we used the mole ratio to get to moles of mercury. We used the molar mass of mercury to get to grams. When you're writing this in your, or typing this into your calculator, it's 1.25 divided by the 216.59, that's the molar mass, multiply by 2, divide by 2, multiply by the molar mass of mercury. So that's all the different functions that you have to do. Depending on your calculator, you may need parentheses somewhere along the way. With sig figs, which remember, we do need to think about those, we've only got 3 sig figs in the problem, so our answer should have 3 sig figs as well. Questions. This was just the example. I have a couple for us to try together. So let me know if I can move on to the next slide. So we're going to try the same problem, but with a different mass. So I want you to try this. Instead of the 1.25 grams, we've got 3.85 grams. Of the mercury 2 oxide. And we're trying to figure out the mass of oxygen produced. And just to help you out a little bit, you'll need the molar mass of oxygen gas. Just use 32 grams. So write out the plan using the generic plan that I wrote out for the first problem and try to fill in everything else. I'll give you a couple of minutes to get started. You probably won't be able to finish it necessarily. If you can, that's great. If you don't, it's totally fine. This is just to we're still using the training wheels and give it a shot. I'm still there. You got your helmet on, your knee pads. If you fall a little bit, you'll be all right. Give it a try, and I'll check in 2 minutes. If you got an answer, You can put it in the chat if you so choose. I'm going to go through and write out the plan first, then fill in the numbers. So if you're still working, that's cool too. Yeah, that's it. So I'm going to write it out so to make sure that everybody has the opportunity to be on the same page. We'll assign our A and our B. Whichever one we're given information about, that's our A. And we know that we've got 3.85 grams of mercury 2 oxide. So we'll call that A. We don't know how many grams of oxygen we have. That's our B. The unknown is what we need. Starting with the number of grams of mercury 2 oxide, we're going to figure out how many moles we have using the molar mass. Then we get to the number of moles of oxygen using a mole ratio. And this takes the form of B over A. So that means it's going to be the oxygen over the mercury 2 oxide. We convert the moles of oxygen to grams of oxygen using the molar mass of oxygen. Now let's fill in the numbers. That's what we're starting with. We're converting to moles. So that means we have 1 mole at the top and the number of grams at the bottom. Next comes our mole ratio. It's oxygen over mercury 2 oxide. Oxygen, we've got 1 mole. Mercury 2 oxide, we've got 2. I gave you the molar mass for oxygen. It's 32. That goes in the top because we're trying to get from moles to grams. Always double check your units to make sure that you put everything where it's supposed to be. First step, we get moles of mercury 2 oxide. Second step, we get moles of oxygen gas. Third step, we get grams of oxygen gas. We've got 3 sig figs here, so our answer should also have 3 sig figs. But if you wrote 0.28 instead of 0.284, you'd lose like half a point. So how are we feeling about these stoichiometry problems so far? If you're not working through the problems, but you're just kind of taking it all in, just let me know that you're here. Let me know you're with me. Just want to hear from you. Let me know how you're doing. I appreciate it. I always like the feedback. I just want to know you're with me. Even if you don't participate by, putting answers in and stuff like that, that's cool. Everybody learns at their own pace. And sometimes you didn't get off work till late. You're in class by the grace of God. I get it. Just want to know you're here and you're with me. That's it. Let's do one more mass to mass problem, and then we'll move on to the next problem type. Feel free to work ahead of me. I'm just going to walk through this one. So if you feel comfortable, go for the gold. Ignore me. Wait for the reveal at the end to see what the answer is. Still working with the same equation, just because I think it's easier that way to get familiar. And then when we move on to the next problem type, we'll change equations. What mass of mercury 2 oxide decomposed to yield 25 grams of mercury? This time we're starting with mercury. We need to figure out how many grams of the mercury 2 oxide decomposed to make that much mercury. Assign the A and the B. The mercury is going to be our A because that's what we have information about. We don't know anything about the mercury 2 oxide. We don't know how much we make or how much we needed to make that much mercury. That's going to be the B. Here's the plan. We move from grams to moles of mercury. We need the molar mass for that. Moles of mercury to moles of mercury 2 oxide. Mole ratio. B over A. Mercury 2 oxide over mercury. Take those moles of mercury 2 oxide and convert to grams using the molar mass. And just as a reminder, I didn't put it on this slide because it was on every other slide. That's our molar mass there. And that's our molar mass for the mercury. Fill in the numbers. We're starting with 25 grams. Moles go in the top. Then we do our mole ratio. It's got to be mercury 2 oxide on the top, Mercury on the bottom. That's our B over A. Then we put the grams on top because we're trying to convert to grams, and moles on the bottom. Make sure that all of your units cancel and it follows along with your plan. And at the end of the day, you should get 27 grams. The key to doing these problems is staying organized. The colors may seem a little bit much to some of y'all, but it really does help to solidify what goes where and in what order. So if you feel the need, if you like colors, if they help you learn, if you're a visual person like I am, I definitely recommend using color pencils, markers, highlighters, something so that you can identify what goes where. And even for your exam, when you do the final exam, because that's what this is going to be on, use all the colorful things. That's mass to mass. The second problem type that we're going to go over today is mass to volume. Volume implies that we're going to be dealing with gases. In my opinion, these are the trickiest ones. And it's because you're starting with one thing and trying to end up with another. So we're going from grams of one thing to liters or milliliters of another. And it's not difficult. You just have to be careful with your units. Just like the last problem type, I'm going to show you the example that I gave and work that through. Then we'll work on some other problems so that you can practice. How many liters of hydrogen are produced from the reaction of 0.165 grams of aluminum metal with dilute hydrochloric acid at STP? We're asked about how many liters of hydrogen. And we're starting with 0.165 grams of aluminum metal. And all this is happening at STP. What we're given here is a mass. And we're asked for a volume. So when that's what your given information is and what the question is, you have a mass to volume problem. This is important. When you identify the problem type, you know which generic equation you're going to choose to help you solve. We're still going to assign our A and our B the same way. A is going to be what you're given information about. That's going to be the aluminum. B is the hydrogen gas, the one that we're trying to figure out. Here's your generic solve it for mass to volume. And I'm stressing it's starting with mass because if we start with volume, it's a different one. Okay? And we're going to go over those too. But right now we're focusing on mass to volume. Here's the generic one that needs to be in your notebook. Starting with grams of A. We get to moles of A. You need the molar mass. You need to get to moles of B. You need the mole ratio. Still B over A. This time we're ending with liters or volume. Doesn't have to be liters. It could be milliliters or something like that. This is the new part. We're using molar volume here. Remember that at STP, 1 mole of gas is 22.4 liters. And from there, we can write 2 unit factors. And I'll show you which one we use when we're setting this up. This is the generic solve it, okay? Now let's fill in our numbers and the variables. Don't want to fill in the numbers yet. It'll be a little bit too confusing. Too much going on. Starting with grams of aluminum. We're going to get to moles of aluminum. Then we'll get to moles of hydrogen gas. Then we'll get to liters of hydrogen gas. And I abbreviate molar volume MV. We're starting with 0.165 grams of aluminum. Molar mass you get from the periodic table. Mole ratio. Haven't done anything new really yet. We're looking at hydrogen gas. There's a 3 in front. So that's 3 moles of hydrogen gas. Then we need the aluminum. 2 moles of that. That's our mole ratio. Then we need to get from moles to liters. We've got to have liters on top. Whenever you're doing mass to volume, that is the unit factor that you use for molar volume. 22.4 liters on top, 1 mole of your gas on the bottom. Go through and make sure that your units cancel properly. And they do. To put this into your calculator, 0.165 divided by the molar mass of aluminum. I'd use parentheses there. Then your molar or your mole ratio, 3 divided by 2. And multiply that by molar volume. And you should get 0.205 liters of hydrogen gas. That's the generic, how do we solve a mass-to-mass problem? Are we ready to apply it to a mass to volume, excuse me. Are we ready to apply that to a new problem? So we've got a new equation, okay? How many liters of oxygen gas are produced from the decomposition of 14.6 grams of sodium chlorate? You will need to remember all the naming that we did in chapter 6, because in these equations, you're going to have, all kinds of compounds. You'll need to remember how they're named and be able to identify them. So sodium chlorate, you'll need to know, is this compound. When we're setting up our question, how many liters of oxygen gas, that's what we need to figure out. And we're starting with 14.6 grams of sodium chlorate. This is a mass to volume, because we're starting with the number of grams of one substance, and we have to calculate the number of liters of a gas. I'll assign the A and the B. Now you can feel free to work ahead of me here, or you can just kick back and watch me work it out. Here's our plan. Starting with the sodium chlorate, we have to get to moles. I'll help you out here. I'll tell you the molar mass. Make sure that you know how to calculate those, though. You need to know that for your exam, and you'll need to know that when you're doing your Chapter 9 homework and the final exam. But at least for now, because we're short on time with class, we only meet once a week, I'm going to give it to you so that you can learn the new concept instead of focusing on the old one. But if you need help with that, let me know. We use our mole ratio to get from moles of sodium chlorate to moles of oxygen gas. And that's going to be B over A. What we need, which is the oxygen, over what we're given, the sodium chlorate. Then we use molar volume to get to liters. That's what we're starting with. First unit factor, we've got moles on top. Grams on the bottom. Second unit factor is our mole ratio. Moles of oxygen gas goes on the top, and there's a 3 there. And there's a 2 in front of the sodium chlorate. Next, we use our molar volume. And that's going to take us from moles of oxygen gas to liters. Make sure all of your units cancel. Then you can type it into your calculator. That's what you would type into your calculator. And do use parentheses to keep things together and have the correct order of operations. When you do all the calculations, you end up with 4.61 liters of oxygen gas. How do we feel about the mass to volume problem so far? We're taking 2 weeks for this chapter, so we will be able to do some more practice next week, just to make sure that we're all on the same page before we finish out the chapter. So if you're looking at this like, man, I don't even know, that's all right. You got another week to hopefully, if you haven't watched the lecture, watch the pre-recorded lecture, because it definitely has more detail than the live lecture, just because there's more time. So let's do another one. If you feel comfortable, you can work ahead of me. If you don't feel comfortable, you can just watch. An unknown mass of sodium chlorate decomposed to yield 30 grams of sodium chloride. How many liters of oxygen gas were produced? Here's our number, so that's going to be our given, our A. And the question is asking about liters of oxygen gas being produced. So we don't know how much of the reactant we started with, but we know how much product we have. We know the 30 grams of sodium chloride. Starting with the mass, calculating a volume. Must be a mass to volume question. There's our A, the sodium chloride, and our B is oxygen gas. Let's write out the plan. We use the molar mass of sodium chloride to get to moles. We go from moles of sodium chloride to moles of oxygen gas using our mole ratio. It's going to be B over A, oxygen gas, over the sodium chloride. Then we use molar volume to get to the number of liters of oxygen gas. I'm going to pause here and give you a minute to try to fill in the numbers. Set up the equation and try to get it into your calculator. If you can fill in the numbers, then that's a really good place to be. Hopefully you've had a chance to fill in the numbers here. I'm going to go ahead and do the same. We have 30 grams of sodium chloride. And you had to calculate molar masses, which I realize is not easy to do real quick. But even if you just had placeholders for those things, you could set up your unit factors and know what goes where. That's great. So that's going to get us to moles of sodium chloride. Our mole ratio B is oxygen gas, and that goes on top. And we get these from the balanced chemical equation. On your homework, you may have to balance an equation first and then use it to do stoichiometry. All the problems that we've done so far, you've had a balanced equation. but that may not always be the case. Last, we've got that molar volume to stick in there. Make sure your units cancel. And I like to have my plan because it tells me what I should be looking for at each step. Now you can touch your calculator. You should get 17.2 liters of oxygen gas. I can look at it again. Rounding. If you put 17.3 and I got 17.2, I would call that correct. We're going to do one more problem, and that's going to introduce volume to mass, which is just flip-flopping our given information. Well, I'll go through this example, and then we'll skip to the reminders, and we'll pick up with volume to mass next time. How many grams of sodium chlorate are needed to produce 9.21 liters of oxygen gas at STP? We're starting with the volume this time and calculating a mass. And that's important because the order of our unit factors changes. Oxygen gas is going to be our A, and the sodium chlorate is B. Here's our generic plan. I'm going to stick with the same color scheme. Since liters last time was purple, that's what I'm going to stick with here. So we've got liters of A, going to moles of A, just like before. And this is going to use molar volume. We need our mole ratio to get from moles of A to moles of B. And then we get to grams of B using the molar mass. So a little bit different here. We'll fill in our plan. We've got liters of oxygen. We're going to get to moles. Then we get to moles of sodium chlorate. And grams of sodium chlorate. Fill in the numbers. This time, instead of having the liters in the top, we need to put the liters in the bottom, because we're trying to get to moles. So that's another difference here. When you're using the molar volume, moles in the top, liters in the bottom when you're going from volume to mass. B over A and then we put in our mass. Everything cancels. And you should get 29.2 grams of sodium chlorate. So not really different. We're just flipping the order of events, and we're using a different unit factor. So for this unit factor, you want to use 1 mole over 22.4 liters. So we'll stop here. I'm going to go to, we just have one more problem too. I'm going to go to the reminders. We'll start with doing that problem next week. We'll do a refresher on mass to mass, then we'll do a volume to mass, and then keep it pushing with Chapter 9. Your exam is going to be available tomorrow, 9 a.m. It will remain available until 11:59. Type out your work. I know it's a little bit tedious. This is the last regular exam. Type out your equation. If you don't have an equation, type out some unit factors for me. Get some credit, because if you don't put anything and your answer is wrong, then you just get nothing. And I want to give you credit for what you know. Your Chapter 9 Mastering Chemistry assignments will not be due until April 18th because we haven't finished Chapter 9 yet. So if you haven't watched the video yet because you have an exam tomorrow, make sure that you watch it between now and next week so we can hit the ground running. Also, we talked about the final exam before. When I looked at the schedule, I didn't realize that distance learning, the subjects A to D, I don't know what I was doing. But it's going to be a take-home exam that we do. And our exam has to be due on Monday, May 3rd. So it's like we finish class and then, bam, it's going to be due. So we'll talk more about this next week. But your final exam is going to be a take-home. I'm going to post it so that you have a week to work on it. We're still going to be finishing up chapter 10, but I want to at least put it out there so that you can be working on it and you know what you're into. We'll talk about that more next time. Don't want to overwhelm you too much, but I did want to put that out there to make sure that you know what you're going to be doing and when for finals week. That's all that I have for you. If you have any questions, feel free to stay behind and ask, or come to office hours, 11:30 to 1 o'clock. Otherwise, you're free to go.